All right, this is the lecture on dependent motion. And dependent means that the motion of one object depends on the motion of another object. And so we're going to analyze what I call straight pulley systems, meaning the cords are straight and they are non-elastic. It's a very important, however very simple and often missed concept that we will revisit more than once going forward. This comes up again and again. All right, so when two objects are tied together with a non-elastic cord, they move together. The motion of A depends on the motion of B, or maybe in this case, the motion of B depends on the motion of A. If you pull on A, it's going to pull B along, such that if that cord is a non-elastic cord, the velocities are going to be the same. That would make sense. The same thing if you're going around a corner in an inclined plane situation, or perhaps, if velocity of A moves down this way, because there's just one roller here, the velocity of B has to follow along, and the displacement of A is going to be equal to the displacement of B in this case, and the velocity of A is going to be equal to the velocity of B. So the way we approach these problems is we're going to define the positions of A and B. We need to define a datum. A datum is a point in the object, a point in the picture where nothing is moving, and we're going to define positive directions. We're going to find the pseudo length of the cord, the length being in quotes, and we'll talk about that in a couple pages here. Then once we find the length, we can take the derivatives once to find the speeds of A and B, and the derivatives again. This is the derivative with respect to time, and we can take that again to find the accelerations. All right, first of all, let's just talk about displacements and velocity. All right, so here is a simple pulley system. Right here, where we're going to pull down on here, you can see that it is a continuous rope, one continuous rope, and we can kind of relate the displacements of F being the hand, the displacement of F going down with the displacement of A, the block, going up by counting the ropes. So let's say that there are 1, 2, 3, 4 ropes actually supporting D, and so we can, by observation, say that the displacement downward here is going to be 4 times the displacement upward. And we do that by just counting the ropes. We say that A has 4 ropes, F has 1 rope. So I'm going to say that the displacement of F with 1 rope is equal to 4 times the displacement of A with 4 ropes. And the velocities are going to be equal, or the same relationship. If you take the time derivative of this equation, you get the velocity equation. And you say the velocity of F is 4 times the velocity of A. Or, another way of saying it, the velocity of A is 1/4 the velocity of F. All right, same thing would happen in this inclined plane problem, where you have 2 ropes being supporting this guy with this little pulley system. So there's 2 on this side, 1 on this side, and we just count the ropes. We have A has 2 ropes, B has 1 rope. The displacement of B on this side is going to go down twice what the displacement of A is. The displacement of B is 2 times the displacement of A. And that's what this is. We take the time derivative and we say that the velocity is equal to 2 times the velocity of A. All right, so that's with a fairly simple continuous rope. What happens if we have a not continuous rope? Here's an example of kind of a 2-rope system where this rope kind of goes around to here and ends there, and then another rope starts here and goes here. Well, another way we can do this is following the P's. This is a concept we used in statics, where you say that I'm pulling down here with a force P, and we know that pulleys just the force on both sides of the pulleys are going to be the same. If the pulleys are not accelerating and if there's no friction or mass associated with the pulleys, you can say that the P here, or the force and the tension in the pulley, is going to be the same on both sides of the pulley. All right, so let's follow the P's. I'm going to say that this is a P here. I got P on that side, and then I follow this around, and I got a P on that side as well. Force P. If I look at the bottom of this pulley, if I got a P on 2 P's on the top, I got a 2P on the bottom. This 2P goes around here, and then if I draw a little section, I can say that there are 4 P's supporting the pulley, or supporting the block B, and 1 P pulling down. So by following the P's, I can just count those. I say A is equal to 1 P, B is equal to 4 P's, and I can say that the displacement of A is 4 times the displacement of B, and the velocity of A is 4 times the velocity of B. Here's another example where we have, this is kind of a not continuous rope, but if we actually look at it, it is fairly continuous. We have this rope going this way, all the way around like that. And they are tied together here. Those two pulleys are tied together, but let's just follow the P's and see what we see. We have one P for point A, and P, bringing this around P and P. And the only point where we have a little transition here is if I have a P on both sides of this pulley, I actually have two P's pulling on this cord here, but then this one would only be one again. So if I draw a little section like that, I can see that the weight C is being pulled up by three P's, where there's one P at A. So counting the P's, I say A is equal to 1, C is equal to 3. The speed of A is equal to 3 times the speed of B. Or excuse me, the displacement of A is 3 times the displacement of B. The velocity of A is 3 times the velocity of B. All right, let's do this one more way, and this is what I was talking about on page 1 of the notes here, or when I first started. Let's define a datum and define a pseudo length. Now, so here's another pulley system. It's got a motor here. It's pulling this up like that. So the motor is going to have it's going to drive some displacement, and I'll call this the length of M, assuming that the length of M just keeps getting bigger and bigger and bigger. Instead of winding around here, we're going to say that that's going to keep getting larger. So there's going to be some displacement associated with that from our datum, which we define there. Let's define a positive direction. Let's just say that it's that way. The positive direction is arbitrary, but it's important to know which direction we define as positive. From our datum then, if that's positive, then the position of A is going to be negative. It's going to be in that direction. Now let's talk about the length of the rope. The length of the rope includes this little segment here, plus this segment and that segment and that segment. It doesn't include this on the other side of the datum. So the length of our rope is going to include this distance SM plus SA, SA, SA. Now these are all negative because they're pointing away from the datum, so I'll say that the length is equal to SM plus 3 times negative SA. If I take the time derivative now, the time derivative of the length is 0, and so the derivative of distance is velocity of M and 3 times the velocity of A, and that's negative because of that. And then I can say that the velocity of M is 3 times the velocity of A, or the velocity of A is 1/3 the speed of M. Similar kind of thing here with this guy, where I've got a datum here. I'm going to call this my datum. I'm going to say that the position of A goes down, well, let's call that positive. So the position of A is all the way down to here if you go all the way to there, but you can see that the length between here and here is fixed, the same length as from between here and here. So I can call this my position of A right there. So I'm going to say that my pseudo length here is going to be these 3 sections of SA. So SA from our datum goes all the way down to here, and I got 3 of them. That's going to be the length of the rope. And then the length of B goes down this way. Again, we don't have to define the actual length. What we're doing is we're just kind of finding the relative, how they change lengths. So I can say that the length is equal to this distance for B plus 3 times the distance for A. Take the time derivative of L. The length is 0 because that's a constant. VB is equal to 3A VA, and I got VB is equal to negative 3 times VA. Now, why is one of these negative? Because I defined that as positive. I'm saying that is moving down that way, but we can by observation see that A is actually going to be moving up like that. So VA is going up in that direction. And so I can say that VA is equal to negative 1/3 VB because of the sign, the SIGN. Okay, so that gives us a little introduction to how to handle these straight pulley systems. Here's a not straight pulley system. This is an example from the book, and we're going to do an example with you today, where this object, it's a person pulling the rope this way, and as he pulls it this way, it's going to go like this. It's going to be, the pulley here is hinged there, which means that it's going to pull the weight up. So the way you approach these things is to define the length of the rope. We're still going to take the time derivative of the rope, and then we're going to use some trigonometry to define some relationships between the speed in the x direction and the speed in the y direction. So I encourage you to look at this example in the book as a good way to approach that. And we're going to do one similar to that with you today. So here is this guy pulling up the boy with the rope hung over the tree limb. And the way this is starting is that the man starts from here and the boy starts from here, such that if the distance between the starting position of the boy and the top of the limb is 8 meters, so the rope in the starting position would go up 8 and down 8. So the beginning length of the rope is 16 meters. And it gives in the problem here that YB goes from here up to here. Oh, excuse me, here's our datum. I should probably put that in there and call it that. Datum is right there, so that Y is defined from the top down. And as you can see, as it pulls up, that the change in Y is going to be a negative number. So we should expect that the change in Y, or Y dot, will end up being a negative number when we get done, because he's moving upward and we've defined positive as down. You can kind of see that in the picture, that there's an arrow here defining that as down. Okay, so what else is in the problem? We're going to say that he's moving up 4 meters from 8 meters. The acceleration of A, he's going to start here and he's going in that direction with an acceleration of 0.2 meters per second squared. All right, so let's draw a couple of things. A moves with constant acceleration. So I'm going to say that the constant acceleration equations apply v squared, v of A squared is equal to v0 squared plus 2a of A times x. If he starts from here, this will be my distance x, defined as positive going in this direction. Positive. Alright, and that says, and velocity of A is going to be x dot is equal to 2ax. Alright, so I have an equation I can get to. Let's talk about the length of the rope. Well, the length of the rope is going to be obviously the length here, and because you started at 16 meters, I can say that the length of the rope is equal to 16 meters. And in our little triangle situation, I can say that this is a distance d, and this distance is y. I can say that 16 is equal to d plus y. So d plus that much y. All right, and then when y is equal to 4, right here, then we got left d is equal to 12. That's kind of our starting conditions. And I can say that the distance A travels, because of my Pythagorean theorem here, I got distance A is 12. I know this distance is 8, so the distance of x, where he is, distance x when he gets there, is x of A is equal to 12 squared minus 8 squared, well, the square root of that, by Pythagorean theorem, and I'm saying that x is equal to 8.944. All right. How about that's the position of A now. That's positive. How about the speed of A? We can say that x dot is going to be equal to, right here, now that I know that position, I can find out that x dot is equal to 2a of A x, which is equal to 2, and given in the definition of the problem is 0.2 meters per second and 8.944, and I'll say that x dot is equal to 1.891 meters per second. Okay, so those are a couple of values we will need in our next piece of it. We'll need x and x dot. All right, now let's look a little bit more at the rope. We said that the length of the rope is equal to d plus y, so let's do that one more time. Length of the rope is equal to, let me put that up here. Length of the rope is equal to 16, which is equal to d plus y. And let's put our, here we go. Let's put d in here, which is equal to, by Pythagorean theorem, we're going to say d squared is equal to 8 squared plus x squared. Back to our picture. D squared is equal to x squared plus 8 squared. Okay, and we take the square root of that. D is equal to the square root of 8 squared plus x squared. Now we have something we can combine with our equation right here. So I'm going to say that I'm going to put this d into there. So I'm going to put 16, take the y onto the other side. 16 minus y is equal to this d, which is the square root of 8 squared plus x squared. Well, let's square both sides. 16 minus y squared is equal to 8 squared plus x squared. Now I need to multiply out this, so I'm going to say that 16 squared is minus 32y plus y squared is equal to 8 squared plus x squared. Let me get that back. Plus x squared. All right. Now I have a relationship here defining positions of y, and to get these into times, we take the first derivative, just like we've done before. We can take the first derivative with respect to time, so dy dt. We do the same, or d dt of both sides of the equation. D dt of both sides of the equation. Whatever you do to one side of the equation, you have to do to the other side. So I'll put d dt right here, and I'm gonna just put a little arrow here to signify this is now the derivative with respect to time. Well, that's a constant, so that's equal to 0. Then I have minus 32 y dot. Take the derivative of time with that, so that's plus 2y. That's the derivative of with respect to y, and then y dot is by the time. That's a constant, so that's derivative is 0. Then I got 2x x dot right there. All right, we're getting closer. I can now factor out the y dot, and what we're looking for, maybe I should have said this more clearly at the very beginning of the problem. What we're looking for is what's the speed of the boy going up when x is at, I guess when y is at that distance. When he's moved 4 meters, what is the speed? All right, so let's go back to that. We're solving for y dot. So y dot is equal to 2x x dot over, factor that out, that would be y dot minus, let's see, I'm sorry, I got 2y on the denominator, 2y minus 32. There we go. I factored that properly. 2y minus 32 on the denominator. Now I have things that I can plug into this. So I'm going to say that that's equal to 2. My x is 8.944. And my x dot is 1.891. And on the bottom I have 2 times y is going to be 4 meters. Minus 32 in the bottom. And then you multiply that out, or divide that out, you get minus 1.409 meters per second equal y dot. All right, well that's how we get started with these dependent motion problems, and we'll talk some more in class.